Hey, what's up, guys? This is Dr. Vivek Velipuram, and I'm bringing you a mini lecturette that explains how to encode branching instructions in MIPS assembly. So there are going to be two aspects that I'll be covering in this video, and those are, number one, how the branch labels are converted to actual offset values. And when we say actual offset values, I mean constant values. And number two, we are going to see how a branching instruction is converted to machine code. So these are the two questions that we are going to address in this particular lecturette. So let's start off with number one, how the branch labels are converted to actual constant values. Now, before we delve into the specifics behind conversion of labels to actual constant values, I would like to give you a sneak peek into the MIPS architecture. I'm going to give you a sneak peek into the hardware of MIPS architecture. Now, the MIPS architecture has a very special register called the program counter. Now, the program counter holds the address of the instruction that needs to be executed next. Now, this program counter is sent to a lookup table, which we call as the instruction register, or rather instruction memory, not instruction register, instruction memory. And this program counter is used as an address, and that address in the instruction memory is looked up, and out comes the instruction to be executed. MIPS instruction to be executed. Now, while the MIPS instruction to be executed comes out of the instruction memory, at the same time, concurrently in the hardware, the program counter updates itself. Specifically, it's incremented by 4. So when a MIPS instruction is going to be executed, the program counter would have already progressed to the next instruction. This concept is going to be very useful and very critical in order to translate the labels of branching instruction to actual numbers. So please make sure to visit this concept. You may pause this video and make sure that you digest this particular fact that PC plus 4 and MIPS instruction to be executed, they all happen at the same time. Now let's consider a very hypothetical piece of code. So let's say that I have a code that looks something like this: add I $t0, $t0, $1, sub $t0, $s0, $s1. And further, I have another, let's say an add, well, not an add instruction, perhaps it's good time to introduce a branching instruction. So let's say branch if not equal, $t0, $s0 to label. And let's say in between, I have some more computations going on. So let's say add I $t1, $t1. Let's say a load word instruction perhaps to $t0, 0, $t1. And let's say that I have another sub instruction, sub T0, T1, T2. And then finally, I have my label placed here at this instruction where I am attempting to increment T0 by 1 again. So let's say that I have this hypothetical piece of code. One thing that you have to remember is all of these instructions have to be stored in this instruction memory right here. Additionally, we are dealing with MIPS 32-bit architecture, and therefore each instruction is going to be 32 bits or 4 bytes. So each of these instructions occupies 4 bytes inside of the memory. And let's consider this hypothetical case that add I is at some address, some hypothetical address, let's say 65536. So the address of the next instruction sub is going to be 65540. Then comes 65544, 65548, 65552. then 65556, and then lastly, label. This instruction which is at the label is going to be at address 65560. The actual addresses actually do not matter because we are dealing with offsets. Everything is relative in this case. Now, let's say my program counter is currently right here. I'm about to fetch this branching instruction. So as the address 6554044 propagates into the instruction memory, and out comes the branching instruction, BNE $T0, $S0, $S1. At the same time, program counter is now updated to 65548. These things happen concurrently in the hardware. So in reality, when branching instruction is being executed, my program counter would have already been proceeded to the next instruction. And therefore, the branch offset is computed with respect to the next instruction. Now carefully observe how I'm going to compute this offset. Since my program counter is right here, I'm going to look how far my label is. My label is present at an offset of +1, +2, +3 instructions. My label is present at an offset of 3 instructions from my current program counter location, which is right here. And therefore, the actual offset in bytes is going to be 3 instructions times 4, because each instruction occupies 4 bytes, which is equal to 12. So therefore, the offset in bytes that has to be used in the branching instruction is going to be 12. So I'm going to replace this label with 12. And that's how labels are converted to actual constant offset values. Now, there may be a case where you may want to branch to a previous instruction. So let's again take a look into that case as well, so that we are well aware of how to consider all possible cases. So let's say that for some reason, I would branch to a previous location. So let me declare a label called PREV, and let's say that for some reason that PREV is right here. When the branching instruction is executed, some things are going to stay the same. My program counter is going to be updated at the same time when branching instruction is going to be processed, and therefore my program counter will be right here. Since my program counter is at address 65548, I'm going to count how far my previous label is. Specifically, my previous label is located at instruction -1, -2, -3. And therefore, in this case now, the offset is going to be -3 instructions times 4, which is equal to -12. And therefore, I'm going to replace PREV with -12. So please pause this video right here. And if you would like, go over it one more time. Next, I'm going to show you how a branching instruction is actually encoded. So let's check out how the branching instruction is actually encoded. And for that, let me just pull the MIPS instruction or MIPS reference material, specifically the MIPS instruction sheet. Okay, all right. So let's say that I want to convert this instruction BNE $T0, $T1, $12 to machine language. Now, there's something special going on in your hardware, and that is this offset value is actually going to be, or whatever offset that you specify for the branching instruction, that's going to be multiplied by 4 by the hardware. The reason is it allows your code to have a greater span. It allows your program counter to branch to farther locations in your code. And therefore, when we encode our branching instruction, we'll have to explicitly divide the label by 4. So we have to divide the label, or let's call it constant offset, by 4 during encoding. So when we encode, we'll actually divide the label by 4 and then convert that to zeros and ones. So since MIPS architecture is 32 bits, so let me create a gigantic array of zeros and ones. So 1, 2, 3, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So that gives you 32 spots right here. Now let's convert this branching instruction BNE to MIPS machine language. So let's take a look into the opcode for BNE. So the opcode for BNE, if you were to refer to the MIPS reference materials, branch if not equal, it's going to be 000 101. So the first 6 bits, 31, 30, 29, 28, 26, 29, 27, 26, 30, 31, 30, 29, 28, 27, 26 is going to be the opcode. That's the opcode. And the opcode for the branch if not equal is 000101. So that's the opcode. The next 5 spots, 25, 24, 23, 22, 21, 22, 21, they are going to be occupied by the RS register. They are going to be occupied by the RS register. So in this case, the RS register is T0. So the register number for T0 happens to be 8. So 8 will get encoded 00010. So that's 8. The next 5 bits, 20, 19, 18, 17, 16 is for the RT register, and T1 happens to be the RT register in that case. T1 happens to be the RT register. So the number for T1 is going to be 9. So 9 is going to get encoded 10010. We are not really using RD register in this case. So that will be all set to zeros. So 15, 14, 13, 12, 10. So 15, 14, 13, 12, 11. It's going to be the RD register. So that can be set to all zeros. So you have RS, RT, RD set to all zeros. Well, I think I have gotten ahead of myself here. There's no RD field in MIPS BNE instruction. Instead, the remaining 16 bits from 15 all the way to 0, 15, 15 so 15, 14, 13, 12, 11, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and one more 0. They are all going to be the offset value. Now, as I mentioned, the MIPS architecture multiplies the offset by 4. So when we are encoding 12, we'll actually divide this by 4, giving us a 3, which will get encoded. So 1, 1, and rest all are zeros. So that's how you would encode a branch if not equal instruction. So branch if not equal instruction is going to have the opcode, RS, RT, and the remaining 16 bits as offset. Whatever offset is present in the instruction, that's going to be divided by 4. In this case, 12 divided by 4 is 3, and that gets encoded. So that's the example that I wanted you to look into. Thanks for watching.